correct something in it. Jeremy came by my office and he pointed out that I had a mistake. He didn't understand it. That's why he came by and asked about it. A translog function is just a function that's so commonplace that it has a specific name, like a Cobb-Douglas production function, or a constant elasticity substitution production function, or a variable elasticity substitution production function. And the advantage is that just by naming it, people know what you're talking about, what form it's going to take. So this is an example of a particular cost function. The idea is that firms can solve a primal or a dual problem, whichever one you want to pick. And that is they can maximize output subject to a cost constraint, or they can minimize cost subject to an output constraint. Either way, it's fine. One is the dual to the other. And then the question that arises is, or from that maximization problem, one of the things that we can derive is the firm's cost function as a function of input prices and the output. If you solve the problem and you substitute away from all the things that you know, you wind up with a cost function that has cost on the left, input prices and output on the right. And that is in the nature of an envelope enclosing the data. So if you had real analysis in your math sequencing in undergraduate, a couple of things that you talked about were the Stone-Geary, the Stone-Weierstrass, and the Weierstrass theorems, and basically the argument is that a suitably chosen polynomial can approximate any function to the desired degree. So if you pick a point on the function and you put a little ball around it, you can pick a polynomial of suitable degree that will pass through the ball on any point on the function that you're trying to approximate. So the question that came up was, suppose we don't really know what the true cost frontier looks like. What would be a good approximation to it, given that we don't really know the exact functional form of the truth? So the approach that was taken was to say that cost is some function of the input prices and output. That you can derive from standard microeconomic theory. And then, since we don't know what the truth is, we could do a Taylor series expansion of the cost function around the solution, around the solution to the true problem. And then treat the partial derivatives in the Taylor series expansions as unknown coefficients. Because you know when you do the Taylor series expansion, you get, for example, you get the derivative of f with respect to pi times pi. And then you get the second derivative of f with respect to pi times pi squared, and so on and so forth. As you do the Taylor series expansion, you get all those terms in. So the thinking was that, well, given that we don't know the true function, why don't we just use a form of a Taylor series expansion around an arbitrary production function? And so the form that's taken by a Taylor series expansion is what we have on the board. So when Jeremy came by my office, one of the things that he pointed out was that we needed this additional line in the function. There were three cross-product terms that I left out. I was in a big rush to get the thing done, and I rushed a little too much and left them out. So I added a line.
What's on Blackboard now is good?
The one on Blackboard is good. Right. I just swapped it out half an hour ago. So if you printed it out at any time today, you better go back and print it out again. The other piece of information that I added is that your data set has more than 145 observations, but you're only to use the first 145 because the remaining observations in the data set are not firms, they are holdings. So the first 145 are all observations on individual firms. Okay? So only use the first 145 observations. And
I was trying to match the data points with the headings. I couldn't match all of them to. That's a previous version of the.
I didn't change the data set. So the data set that you have out there, because you printed it out, that's what, yeah, you put yours in a spreadsheet. I don't know how to keep this. In any case, the columns are an ID number, is 1 through 100 and 218. Oh, okay. So I'll only use 145 of them. I didn't realize that at that day. So there's an ID number, just an index, the year, it's 1970 throughout. The next column is cost. I don't know what unit it's measured in, billions of dollars, millions of dollars, it doesn't matter, they're all the same. So if the first entry in the cost column is 0.2 times 10 to the 6th, then all the others are 10 to the 6th, and we know that moving the decimal doesn't affect our regression output at all. So it's cost, Q is quantity, PL is the price of labor, SL is the share of labor. So if the total cost is 100 and we spent $43 on labor, then 43/100 is the labor share. PK is the price of capital, SK is the share of capital in total cost, PF is the price of fuel, and SF is the share of fuel total cost.
So share of capital.
Q is quantity, PL is the price of labor, SL is the share of labor, PK is the price of capital, SK is the share of capital, PF is the price of fuel, and SF is the share of fuel. So it looks like in your data set there are only three inputs: labor, capital, and fuel. We'll come to why that is in a minute. What I mean by share is if we take the price of capital times the quantity of capital that we hired and divide by total cost, that's capital share of cost. Could be the share of capital, share of labor, share of fuel, all the same, done the same way. So the price of the input times the quantity of the input divided by total cost.
Q is different for labor, capital, and fuel?
Q is output.
Output.
As in quantity. We're going to come to that in a minute.
So share is like
Labor share is the price of L times the quantity of L that you hired over the price of L times L plus the price of K times K plus the price of F times the quantity of F plus the price of materials times the quantity of materials that we hired. But we don't have materials in this data set, and I'll come to why that is in just a moment. Okay? Well, you weren't the first one to ask.
Or you could just say total cost on the denominator, which is actually...
Yes, that I also said several times, but people didn't seem to be having trouble getting the message.
Which is what you actually gave us as total cost.
Right, I gave you total cost. I'm just telling you where the share numbers came from, okay? And don't waste your time trying to figure out how many units of capital we hired. You don't need to know that. All the data manipulation has been done for you. You don't have you have to take logs, okay, because that's what it says over there. You've got to take logs of the data. But all the other manipulations have been done for you. Somebody else put lots of time and effort into manipulation of the data and constructing the data set. Okay? So you don't have to do that. So now let's proceed. So this is an approximation to a factor price cost frontier that can be derived from a standard firm's output maximization or cost minimization process to derive from. It's in whatever your micro theory book was for Bowman. It's in variant. I know for sure it's in variant somewhere. It's been more than 20 years since I read it, so I couldn't tell you the page number, but I'm almost certain it's in there. In some shape or form, it's in there.
Did you use variant?
So, the nature of the problem that's being solved in order to create that factor price cost frontier is to put fuels on an axis and labor on an axis. And you know from your micro theory class that the firm has an iso cost curve, and they also have an isoquant. So iso cost meaning that every point on the downward sloping straight line corresponds to the same level of expenditure on input. Isoquant means that every place on the convex line corresponds to a given level of output. So they are both what's known as a level curve. And we know from micro theory that our firm is going to pick F star and L star. And given F star and L star and prices of fuel and prices of labor, we can figure out what they paid, what it cost them to produce the quantity Q. Or we can turn it around. Given a set of prices and a quantity that they want to produce, we can figure out the least cost way to do it. In either approach, we can derive this factor price frontier. In Bowman's class, when you solve problems like that, and I'm sure you did some of them, you set up the first order conditions and you derive the demand for capital and fuel and the demand for labor, right? From those first order conditions, we did that. And then you talked about maybe from this first order condition, you derive the demand curves, and then you talked about cross price elasticities, you talked about things like the marginal rate of technical substitution, and so on and so forth, right? And you got all involved in Jacobians and Hessians and bordered Hessians, Vermeer's rule, and all that stuff. Well, you use those things. Whatever they are, you use them. In order to, the bordered Hessian, remember, has the second order conditions in the body of it, and it has prices of the inputs in the last row and the last column, and a zero in the last row, last column entry. Remember that? And the Jacobian with the matrix of first order conditions, the coefficients for the first order conditions. And then when you wanted to solve for the demand curve, you used Vermeer's rule. You'd swap the prices into the column that corresponds to the input for whose demand you were searching. And then the demand curve was the Jacobian over the Hessian. You don't remember doing all that? Maybe we stopped doing that decades ago or something. But we had to